Hi there, let's get into some less spherical code. The simple harmonic oscillator is very relevant in nature, but the damped harmonic oscillator is more realistic in most of the situations. When we talked about air drag, we used a friction force proportional to the velocity. If the velocity is small, air friction depends linearly with velocity. But if the velocity is large, then a better description should include powers of the velocity. Consider a spring of constant k oscillating in a light medium. It could be air. We can describe the effect of the force of friction as minus bv, where b is a positive constant that depends on the fluid and the shape of the object. The fact that this force is linear in the velocity has all the numbers to make Newton's second law integrable. Let's write Newton's second law for this system where we have a recovery force minus kx and a friction force minus bv. I rearrange this expression. The square root of k over m was the natural frequency of the simple harmonic oscillator, so I will call it omega naught, and I introduce a new constant beta so that this equation is rewritten as here beta and omega naught are positive constants. What is the solution of this differential equation? Let me guess an exponential as the solution and let me write the most general form of that, which is a times e to the at plus d times e to the dt. Let me check this solution in the differential equation. I substitute these derivatives into the differential equation. I separate the terms with the exponential to the at, Then, because this square root also has the unit of 1 over a second, I will call it omega prime. This simplifies the writing of the solution as this is the solution for the motion of a harmonic oscillator with damping. Let's have a closer look at it. The first term, the exponential with beta t, is a decreasing exponential which is a clear signature of damping. But for the other term, we can have three options depending on the relationship between beta and omega naught. Option 1, on the damping. If beta is smaller than omega naught, then omega prime is imaginary. I introduce omega 1 so I can write omega prime as I omega 1. I can write then the solution as e to the minus beta t times a times e to the I omega t plus b times e to the minus omega t. Using the relationships between trigonometric equations and exponentials, we can rewrite this as e to the negative beta t times a times the cosine of omega 1 t plus phi. Here the constants a and phi are found using the initial conditions, business as usual. This last equation is very clear to read. It has an oscillatory behavior through the cosine, but this exponential term is going to damp those oscillations, so they'll die away eventually. We can represent this solution and plot the position as a function of time. This is a sinusoidal plot in a decaying exponential envelope. The angular frequency of the oscillations is the square root of omega naught squared minus beta squared. Well, strictly speaking, we might not be allowed to call this angular frequency, as the motion is not really periodic. But if we consider that the motion reaches a point with zero velocity with a constant periodicity, then we might accept to call it angular frequency. The period T1 is 2 pi over omega 1. This angular frequency is smaller than the natural frequency of the simple harmonic oscillator. If beta is close to omega naught, then we lose the oscillatory motion. The position decreases without crossing the origin. If beta is very small, we lose the damping behavior. It will only be manifest for very, very long times. We can think this equation as the cosine term multiplied by a decrease in amplitude. The amplitude of the oscillations decreases exponentially. A of t is a times e to the minus beta t. The ratio between the amplitudes of two consecutive oscillations between two consecutive maxima is which is constant. It does not depend on which number of oscillations we consider, because the potential energy is proportional to the square of the amplitude. Remember that for the spring it is 1/2 of k amplitude squared. We see that the energy of this damped oscillator is not constant. It is being lost to the fluid. It is being dissipated as heat or radiation. This damped harmonic oscillator is a very common system in nature. We'll see some examples a little bit later on the course, but before we complicate this system a bit more, let's go to the other two cases of damped harmonic motion. But that will be in the next video. May the science be with you.